it was a pleasure to introduce you. It is a pleasure to introduce you, Giorgio Senesi. He's at the moment one of the most important researchers. Yeah, it's true. Researchers working in LIBS, and he was talking a little bit about his track, his experience. But what I can tell you that we had the first meeting last year in Pisa, where there is another group that is run by Vincenzo Palleschi. Is strongly collaborating also with Giorgio, with the CNR. Is working with us, with our Archechemis unit, and today is a really very good pleasure to have here, because we can start this hopefully new collaboration. And first, I'm grateful because he is here to talk about this analytical method. This is a kind of new method, just start to be developed in the portable as the portable device since the 2010, 2010.
Right. Yeah, the portable.
Portable, yeah, 2010. So this from our Archechemis aim research is very important, because this technique is able to see some kind of element that for us are very important, because are characteristic from an important line of research, like light element, but also rare earth element. So it's a great pleasure to have you here, and just we will enjoy this hour listening, and if there are at the end some questions we will ask. Really, thanks and welcome.
Thank you so much. First of all, good morning, ladies and gentlemen, and thanks for being here. I want to thank for his kind words Professor Gallello, Gianni, we call him, since I would consider him a friend, even if we don't know each other for a long time, but I think we have shared a lot of things in common in these days, and even the few days that we met in Pisa. That's the reason why I'm here. Well, I was introducing myself a little bit, but just to give you an idea, what my background was quite different. And then I was, just for the one that missed, but I just arrived at the point that I start working with this analytical technique that today I'm gonna talk to you. The idea, I structured this talk in a way that, just giving you an overview. In the first half, I would say, where I'm just pointing out some attributes, obviously, first the positive things, and then some history, some origin. It's a long history, it's not so recent, but even if it's not been developed so much in some scientific fields. And then I will go through a little bit the LIBS process, how this works, and just focusing on what we can get. So from qualitative to quantitative analysis. And then I will bring just few examples of my experience in these 20 years about using LIBS, from the benchtop equipments to the new advanced portable systems, even commercial systems that nowadays are currently on sale. And so I hope I'm not gonna get bored you. I'll try to keep it alive. Anytime you have questions, you can stop me. I'm not afraid about that. So, okay, thanks again. And so let's go on. And the first thing is, what is, from now on, I will call it, obviously, to reduce the time, LIBS. So it's laser-induced breakdown spectroscopy. I will go through also the meaning of this combination of words, but you will see during the presentation where we come through all the explanation, there is a meaning about that. So what is it? It's just an optical emission spectroscopy technique. Basically, we use a focused high energy laser. Generally, for all the common LIBS systems, we use a neodymium YAG source, and it's used to focus the laser on a sample in order to vaporize, so ablate, remove a small amount of your sample and create a plasma. This plasma is what I was saying before, it's a fourth state of matter, so it's just a plume, small plume, where you have atoms, electrons, ions, and even molecules around and colliding each other, even with the surface. And these ones are giving then an emission at the end of the pulse, of the laser pulse, then it's collected by a spectrometer and it's getting out a spectrum, giving our information, I mean, the information about our sample. So what we could do is really have fast analysis. You will see, really few seconds you need. I mean, even if you use one laser pulse, to be less than 1 second, the acquisition. We can get, it's really nice, simultaneously, the element detection and quantification. So, I mean, with this laser pulse, you can get all the spectrum with all the elements emitted and present on our samples. We can get also microscale compositional imaging. We'll see, that's one of the figures of merit in terms also speediness of this technique. There is the nice thing that we could do depth profiling. So we could do a stratigraphic analysis, shot by shot. So we can go depth and see how the composition is changing in terms of the elements, you know. And this could be applied, as you can see here, basically on gases, solids, liquids, and even aerosols. Obviously, the setups are changing, there are challenges and things, but in principle, I mean, there are studies done on all of these states of matter. Okay, so as I said before, the advantages, here we go. So we basically with a typical LIBS spectrum is going from the UV range, talking about 200 nanometers, up to the near infrared around 900, 950 nanometers. So with a single laser pulse, you can get all this spectrum in this spectral range, and all elements, obviously emitting light, could be captured, okay? And this will give us some qualitative or quantitative information on the sample present in our samples. So one of the nice aspects is that I would say that the system and the setup is quite simple. You have 4 main components. You need a laser, you need an optical path, you need a detector and spectrograph to collect, you know, and then transform the information in the spectra, and a computer to process your data. This is for sure, the second point is for sure one of the figures of merit, the top figures of merit of the technique compared to many other analytical methods. Keep in mind that the first competitor of LIBS is X-ray fluorescence, because it's elemental technique, so they both join together. There are differences. I'm not gonna go through because I don't have time, but I could give you some replies, or if you have some doubts, I can tell you the differences later. But for sure, we can get light elements. I mean, this means that we don't have to use vacuum. I mean, we can get these elements shooting in the atmospheric air. This means lithium, beryllium, boron, carbon, and so on. Obviously, for some elements, there is the trick of the air presence if you are looking about the amount, okay, and the content. But that's something that could be overpassed. We need really a small amount of the sample. So we're talking about picogram or nanograms is removed by the ablation and vaporization, okay? The analysis, as I said, is really fast. For one laser shot, you can get, as I said, less than 1 second. But even if you are doing multiple laser shots, you can stay in less than a minute for sure for a lot of spectrum. One interesting aspect that not many others technique has is that we can really analyze ultra-thin alteration layers, for example, and this is why, because we are using a laser, and the laser, once is hitting our sample, is creating a shock wave. So this shock wave is removing any layer that, I mean, is not desired in our analysis. So we could remove the dust or anything contaminating on our sample and then start the analysis. We could do, as I was telling in the beginning, some stratigraphic compositional analysis. We could reach 100 millimeter depth, and this could be performed even in situ, since the focus of the laser could be really restricted. I mean, this depends from the technical parameters using in every setup, but we can go really small in terms of analyzing. For example, I will focus all of these about geomedia materials in this talk. Okay, so I didn't say that, but the title was quite explicit. So I'm just focusing basically on rocks, minerals, and even soils, all related to the environmental samples. So we can go focusing really on small grains or even in some liquid or solid inclusions inside rocks or our minerals. We can get, as I said, some compositional imaging in rock or other samples, even at really fast rate of acquisition. Kilohertz means that there is people using the technique in the mining exploration. So they are getting out drills of rocks, and they are able to acquire in less than 1 hour really full drill of 1 meter long for maybe 20 centimeter wide. So it's really something that could help in terms also of what you can do screening, saving time and cost. That could be used in extreme environments, as we have seen. The most probably famous example is the use of this technique on Mars. I mean, we have nowadays 3 missions on Mars. The first mission from NASA, the second mission, the third mission is related to the Chinese guys, and even on Moon, the Indians people, they sent one rover mounting the LIBS. So LIBS was quite useful for sure to detect the elemental composition of rocks and soils on Mars. I mean, with LIBS, we discovered the presence of hydrogen. Hydrogen was just on the dust of the Martian dust, and was on a top on a common basaltic rock that we could find even on our planet. But we were able to distinguish the hydrogen due to the presence of the dust. And the other nice aspect is that we could combine this technique with other analytical techniques, like laser-induced fluorescence, Raman, laser ablation ICP mass. And this, because we can get at the same time, even information about the molecular analysis. That's something that barely you can do with LIBS, even if you can get also with LIBS molecular information, but it's not the straightforward detection. So some story about, LIBS. Since the invention of the Rabi laser in 1960, the laser-induced plasma was observed, But what happens that in 1962, those two authors, Branch and Cross, they were the first to mention the plasma as a spectral source. That plasma could be used as a spectral source. And then in 1963, we had the first manuscript talking about spectrochemical analysis on surfaces. Okay. Then in 1968, there was published the first review about spectrochemistry. They were not explicitly talking about LIBS as we know it nowadays, but they were talking about laser spectrochemistry. So it was the starting. At the same time, the spectrochemical applications were developing, but there were also the side from the theory and modeling of, in order to understand these low energy laser-induced plasma process, because the process is still under investigation. It's quite complex because it's a mixture of physical and chemical processes together. And in 1965 was published the first study about, the process is active in the laser plasma initiation and the development in air of the plasma. And then in the 1960s, early 1960s, Graham published, this is kind of considered like a Bible for this sector regarding the plasma spectroscopy. But so in the late 70s and 90s, applications of LIBS start growing up, but only in the early 80s, specific research laboratories start working and applying and studying LIBS more detailed. The first commercial instruments was sold in the 90s. Nowadays, obviously, there are several companies selling several equipments all over the globe. But going to the name, the laser-induced breakdown spectroscopy was officially introduced by these two guys, Radziemski and Lurie, in 1981. They were from US, they were working at the Los Alamos laboratories, and they were the first to use this name and giving to this technique this name. Only in the late 80s, the technique arrived in Europe, and it took the name, was renamed. We like to change the names here and make confusions. Was renamed laser-induced plasma spectroscopy. Well, I mean, the breakdown, it's something, I'll show you why it's breakdown. But they like much more, and probably was much more direct, the idea of laser inducing, and then we have a plasma, and then there is the spectroscopy coming after. But this ambiguity, there are a lot of papers. Nowadays, there are still people using LIBS. Few of them, I would say. It's much more common for the most of us to use LIBS. But only in the first international conference, all in Pisa by Vincenzo Pallestri, who is a guru of the technique. Back then in 2000, they just decided to uniform and try to use only one identification acronym for this technique. Well, this is not really updated, but it's just to give you an idea. I was lazy to do it. But in 2019, it was published one article, every 1 hour, in one article published every 15 hours about LIBS. So it's just to show you how is growing up the use of the technique. Well, let's see now a little bit about the LIBS instrumentation, how it is done and how it works. As I said, it's quite simple, the setup, and we have, first of all, a solid-state short pulse Q-switch laser. This is fundamental for the material ablation and to generate the plasma. As I said, generally, all the LIBS setups, even the commercial ones, they use neodymium lasers. And generally, they use one wavelength that is called 1064 nanometers. So it's the fundamental wavelength because it's the much more useful and versatile for more applications. We need, obviously, the optics to focus the laser light on the sample, and even to collect the light with the fiber, we have to catch the light. And so we use lenses or mirrors, specifically these in a benchtop equipment. But even in the commercial ones, they have to use at least one lens, or there could be a sphere lens or a ball lens to catch the light of the plasma and to focus the laser on the sample. Then we use a spectrometer and the detector system to collect the signal and to discriminate the plasma and the light emitted from this plasma. and then obviously a computer to control the data acquisition and for the processing. So this is just a sketch to show you. Here we have the laser, the beam. Generally, you have a lens here that is going to focus our laser on the sample. We have our plasma here. The fiber is catching this light, sending the signal to the spectrometer that is solving it in a spectrum where you have on the x-axis the wavelength, and on the y there is the emission intensity that is given by an arbitrary unit. And this is just to show you that the intensity is proportional to the concentration of the component in the target material that we're going to analyze. Those are some really generic conditions, but just to give you an idea of some numbers, see the infrared, the first wavelength is the most common one used as laser wavelength. The pulse energy could vary a lot. It's just to give you, again, just an idea, but from 10 to hundreds of millijoules per pulse. There is the laser pulse duration could even is around 6 nanoseconds, but could be 8. The repetition rate could start from 10, but reach even the kilohertz, and then power density, but also the focal spot size, for example, could go from few tens of microns to even hundreds of microns. For example, the spot size on Mars generated by LIBS is about 300 microns, okay? And it's focused at 7 meters of distance. So just to give you an idea about images, this is a classical benchtop. See 2 lasers occupying a full table. The optical path here, the fiber up on here. This was set up for an experiment in the liquid. We have a lens up on here to focus the laser down there. And those are some commercial. You can see some really benchtop, some portable, transportable, I would say, with wheels. This is kind of first idea of the standoff system, what then applied on this guy here, the rover sent the Curiosity, the first sent on the first mission. On the top here, you have the CAN that is containing the LIBS. So the laser is shooted from the top here down to the floor, to the ground. And then we have the first developments also of the portable handheld systems. The first ones were coming with cables, like umbilical cables, and just have the source on the top or a backpack. For example, this was used by the people from Malaga, from the group of Paterna. They used this to analyze the Cathedral of Malaga. They use this backpack portable system of this one. And this is the last generation of the handheld, the commercial handhelds. So let's have a look at the LIBS process, how it is working. The cartoon is related to a rock. That's much more funny for me. So what we have is a pulsed laser is focused on our rock, and parts of the laser energy is really absorbed by the rock, and at this time is just generating ions and electrons. So there is stage of absorption. Then all these emitted free electrons collide each other with the photons of the lattice of our sample. And this is giving, obviously, is heating up. At this stage of the heating, we reach a level of heating where a small portion of the target, really reaching free electrons and ions and neutrons, is ablated and vaporized. You have to keep in mind that this is the stage where we need the sufficient energy to break the lattice of the sample. And that's why it's called breakdown threshold. So the breakdown is coming from this threshold that we need to break in order to get the informations useful for our plasma and to generate the plasma. Because the next step is exactly this one. We are going to have the plasma formation. So while the vapor is still expanding during the laser shooting and the optical energy is absorbed, we have the formation of the plasma plume, okay? And this plasma could range from 30,000 kelvins in the early times, and after its formation, it could decrease fast to 5,000 kelvins at the late stages. And now at the last, once the laser pass ends and the plasma plume collides with the surrounding species, what we have the emitting of the radiation with the cooling, and that's the time when we can collect our signal to analyze the rock in this case, and so we have the species formation. So the entire process really lasts up to tens of microseconds. So it's really important now, you will see, to catch the right gate of acquisition, because there is a temporal, as you will see, there is a dynamics of the plasma is done in this way. I mean, you first start with a broad emission. You have seen that light, white light in the cartoon. In the first cartoons, there is a white light. It's given by the intense continuum emission. So this light is not giving any signal. It's just continuum. It's just noise. But that noise is even important for our spectra, for our spectrum, because it is containing the information that are unique of the sample that you are analyzing. And then the plasma is cooling down, and at this stage, the continuum emission decreases, and we have the first ions forming, so we can see the first peaks coming out until reaching the narrower emission peaks that what we want for our quantification, I mean, for our analytical purposes. And that's an example just of a peak to see. So the evolution is this one. You start from the background emission, like a tenth of nanoseconds, and then you see improving the time, we go to something, it's forming something till reaching, for example, in this case at 150 nanoseconds, a nice narrow peak that would be useful for our analytical purposes. Obviously, there are factors affecting this formation of the plasma in the LIBS. And which are these factors? The laser characteristics. These are related to the features of the company that we bought the lasers. The wavelength, because I've been talking about only the first wavelength, the fundamental, but common studies in the lab used also different wavelengths that could be useful for different kind of analysis related also to the samples that you need to analyze, like the green, the second harmonic, so talking about 553, and the UV also. Those are much more smooth. I mean, they are not so aggressive in terms of the destructiveness, micro-destructiveness of the sample. So it depends. If you're working, for example, with gems, you don't want to destroy it. So you're trying to keep as small as possible the damage, for example. Or obviously, there are chemical composition of the target material. This, as I was saying now, the time window of observation, as you have seen, the temporal evolution is really important. We need to control that. Otherwise, we are not able to check the right emission intensity in order to be useful from an analytical point of view. The geometric setup, it means the distance from the lens to the sample. There are lenses that are focusing, even the lens that is catching the light of the plasma has to be correct, because the light of the plasma has to be acquired fully, entirely, and not a portion. Otherwise, you're not looking specifically what you are detecting. That's common to many analytical techniques, the matrix effects, obviously, and then the ambient conditions like atmospheric pressure, temperature, and so on. All of these really determines whether the laser plasma generated is, as I said, analytically useful. Okay, what's the goal? So the goal of this technique is to generate what is said an optically thin plasma that has to be in the local thermodynamic equilibrium state. This means that the composition has to be the same of that of the sample, in order that the ablation can be assumed to be stoichiometric. So it's really important that the observed spectral line intensity has to be directly correlated to the concentration of the elements in the sample. And that's why, I mean, every measured LIBS emission spectrum is really a geochemical or a chemical fingerprint of your sample, and it's really unique. It's really a fingerprint. And you will see in many applications, this is really has been confirmed. So just to give you an idea, it's really a general idea, don't keep it strictly, but it's just to give you an idea about the elemental sensitivity in the periodic table. You see, obviously, the figures of merit is about the light elements, but we have also good results in terms of what we can get with the metal transitions and so on. Well, like every nice rose, there are also thorns on this side, and I'm gonna say which are the thorns specifically for some applications. The first one is that sometimes the small laser spot size could create a complication. In which terms? That if you are going to consider back analysis of a rock, obviously if you have a spot of 100 of microns, you're just maybe detecting, if you're staying in one position, just one mineral inside a rock. So even if you are not thinking to study the composition of that mineral specifically, you cannot assume that that composition is related to all the rock. And this is something that happens, has been, I mean, it's common to see some articles published with people studying in this way or trying to consider in this way materials. Obviously, these could make an exception if you are looking at fine-grained materials, because those are much more homogeneous in terms of size. Then obviously, as I said, the matrix effects, both the physical and the chemical, those they could affect the intensity measured. And we know this is common, as I said, for many techniques. Regarding the chemical matrix issues, obviously is related to the fact that one element could influence the plasma emission behavior of another element. So how could I solve this? There are many ways. I mean, there are some ways to do that, but you have to keep in mind that the lucky thing is that in a LIBS spectrum, you can get many emission lines of one element. So you can be lucky if you're looking at some high amount content of some elements that you can choose the correct line without any interference. For the physical matrix effects, this is due obviously to the nature of the sample. It depends from the grain size, porosity, degree of crystallinity, roughness, hardness, reflectivity, and so on. All of these, they could determine the amount of mass ablated by our laser. In this case, there is a way, I mean, generally what we do, all the people, what they do to avoid this and ameliorate our our investigation, we acquire hundreds or even thousands of laser spectra in order to reduce this matrix effect. That's common, again, for many other analytical technique, but obviously LIBS is not accepted at all. If we want to get accurate quantitative analysis, we have to use standards that could match our samples. This means in the concentration range, these are common things you know already, better than me probably, but that's obviously, it's also for LIBS. And then keep in mind that if you're working with cultural heritage, you're working on your painting, maybe you have to be careful because it's being well invested. I mean, even if the spot size you can barely see by your eyes, but you're removing something. Generally, people that is working with LIBS on paintings, they shoot on the back of the painting, you know, just to get some information. Obviously, they don't go, they don't have the permission anyway. They will not have it. And the last point is something that it's less frequent nowadays, but was much more frequent in the past, because now I would say that those kind of issues are being overpassed with the technology quite a lot in terms of really huge development of technology. The lasers are way much stable nowadays than 20 years ago when I started. We were keeping all the time measuring the laser energy in order to do not have variations, and so changing everything, so messing up everything. Okay, so what we can get? Data analysis. We can get some identification of the element by the emission lines from the spectrum for qualitative analysis. So we acquire spectra from, like here we have first sample a limestone from my town. It's really common. A Binny sandstone from Edinburgh in Scotland. It's really common rock also there for all the monuments that they have there. And this is a red clay soil. You can see in these spectral ranges how many lines you can get. I just identified some elements for some lines. But if you go here and you enlarge, you will see other lines. You can even get 200 emission lines in a spectrum like this. Okay. Obviously, what we do is that specifically we try to do a preprocess of the spectra once acquired in order to avoid any signal intensity fluctuations, even by other techniques. And we do this accumulating multiple shots, as I said before. And there are also other issues beside this, like the differences in the spectrometer resolutions. Obviously, not all of us could have enough money to buy the most fancy equipment. So you have to overpass some of these with other escamotages. I mean, find other solutions or try to keep in mind these. There are the spectral interferences, the sample characteristics also, and even the effects from the external environment. All of these has to be keep in mind before using our spectra. So the spectral normalization is really important and has to be performed every time also to avoid the matrix effects. And I'm just giving here just few examples. For example, this is a spectrum coming from an obsidian. You see here the background, how is high. I'm just highlighting this area here. Down here, you have the row. See, it's not online on the zero. And then we apply different methods, smoothing, normalizing, or removing the background in order to have all flat and removing the emission continuum that could then force our quantitative analytical analysis. What else we could do? We can get quantitative analysis. Here, there are also what we do to get some high precision accuracy, since these are also affected by these factors here, these parameters, and we try to optimize those in the acquisition stage, specifically if we're talking about advanced top equipment. Obviously, nowadays, the commercial ones, you cannot do too much about, for example, the lens to sample distance is fixed. You cannot move it. I mean, they optimize everything. So you have just to go there, press a button and shoot. But in the lab, we were used to manage all those things to optimize and maximize the analytical performances. But these are something that still are, things to keep in mind once you're working for these. And even, those are not dependent on the sample, but are depending by the sample procedure. So it's important once, if you're working in your lab, to keep in mind of these issues. So I'm gonna just show you the three most common methods. The first one is the calibration curve method used for ICP, for X-ray fluorescence. So, the unknown concentration of an element in a sample set is determined by comparing the LIBS emission intensities acquired in our sample and the set of standard samples of known concentrations in order to cover the expected range of the unknown concentrations. Otherwise, I mean, it's like a cover of Linus. You will have something underestimation or overestimated elements. And here I'll give you some example of some construction or calibration curves. Here we have copper content detection inside 3 rocks: andesite, diorite, and monsogranite, all igneous rocks. And you can see how they're standing about the linearity of the curve. On the other side, there is 3 or 4 lithium minerals, petalite, spodumene, and so on. And you can see how nice is coming also the fitting and the linearity obtained with LIBS, and compared obviously to the reference, in this case, to a reference technique. One case I think was ICP here, and probably here X-ray fluorescence. So the calibration curves really relate the measuring intensity of our elemental peak in our spectrum to standards of known composition. And this has to be obviously measured under the same conditions. Otherwise, I mean, this will make no sense. Another method really specific of LIBS is called calibration-free. The calibration-free method is really a different approach because it's avoiding the use of standards and was developed to address the sample matrix issue. So the calibration-free procedure is based on the assumption that the local thermodynamic equilibrium condition is established inside the plasma that we are generating with our system, LIBS system. To do this, we have to calculate the plasma electron temperature and the electron density of our plasma. And those information, they will give the elemental composition of the based on this information and the assumption that they are in a strictly range, this they will give us quantitative information. The calibration-free, it's nice, but for complex matrices, we tasted and is working, I mean, as I said before, like a cover of Linus. I mean, you can get some nice quantification for some elements, but overestimation or underestimation for other elements. Is working really nicely for alloys. Once you get like 2 to 3 elements, it's working precisely. But otherwise, for more complex, is quite difficult for my experience. And the last way to obtain quantitative information is obviously to use the chemometric analysis. One of the first work was back then in 1994. But the reason why is because if you consider that in one LIBS spectrum, you can get even more than 20,000 variables. So it's a lot of information that could be played by algorithms. And I can tell you that nowadays there is most of the literature is doing this, acquiring the spectra and using chemometrics to do discrimination, classification, try to understand the origin of the sample, to distinguish the nature. And in most cases, I'll show you also some examples, you will reach 900% higher, even higher accuracy, but you're starting from 900%. So it's really, back then, the information contained in the spectrum is really unique of the sample in order that these could be used to really do high standard quantification. Obviously, the chemometric methods are also used for the signal analysis, but also for the spectral preprocessing to help us in these steps. And only after to the data processing and even interpretation. So we could use simultaneously different variables to get the noise reduction and mitigation effects from interfering signals, identification of outlier analysis, or develop calibration, and then extract the maximum information from our data set. So all of these could be used applying these methods. And nowadays, the multivariate statistical analysis has been really widely used to infer all chemical information contained in the LIBS spectrum. And much more is really opening a new path for semi-quantitative and quantitative analysis. Here is just a table with some of the acronyms. Maybe you're not familiar with some of them, but just to show you how many algorithms could be used only for spectral data preprocessing, for the qualitative analysis, for quantitative analysis using univariate calibration, multivariate calibration, and then even for the calibration free. So there is a lot going on this. Now, obviously, one of the, still nowadays, I mean, there is people complaining, but we know this, one of the thorns is the poor limit of detection or sensitivity, okay? This is something that we every day and in all these years has been trying to progressing with different methods and way or solving this issue. And it's going over and over, so getting better and better results. So what we do to enhance and to reduce some limitation of the sensitivity, sometimes we introduce a purge gas around the plasma. So the plasma is confined inside an inert gas to intensify the signal. Or we use a double pulse excitation. It means two lasers, changing the geometry of the lasers could be collinear, perpendicular. There are many differences given different times. The first one is generating the plasma. The second one is reheating that plasma generated by the first laser pulse in order to have an intensity emission. And then we have the magnetic and the spatial confinement is another way to have the plasma confined inside a magnetic or an electric field in order to intensify the signal, or by a glow discharge or microwave, spark discharge, even, or using nanoparticle enhancer. So you use nanoparticles from metals like silver or gold coated on your surface, and this will enhance the signal. Or even surface enhancement that is similar to nanoparticles, something that enhances the surface acquisition. All of these are methods that could be used to increase the sensitivity. Okay, and now let's see some limit of detections from this table. The accuracy of LIBS data is, I would say, generally greater than 10% in relative standard deviation, okay? And the precision is often greater than 5% in relative standard deviation. The loads are ranging from 1 ppm to even higher than 100 ppm. It's really changing due to the materials that you're analyzing and also to the setup that you have in your hands. But this is just to give you an idea. As you can see, many could stand less than 100 ppm. Obviously, it depends what you're looking for. And that's the first question. Every time that you're using an analytical technique, you have to do some questions to yourself and understand if the technique could be useful. I don't think there is one only analytical technique that could solve all the issues, and this is not the case of LIBS, but a combination of different techniques obviously could help to solve the problem or to detect better or to understand better what we are looking for. And so the laser-induced breakdown spectroscopy, as you've seen, is the ideal candidate for different applications due to the fast collection of the data, to the versatility, and even for the configuration. Here we see in the field, and we see on Mars. Here there is using for drill cutting. The LIBS system is here mounted. Here is underwater system for hydrothermal acquisition on some sediments. So obviously, all of these applications need to develop a customized LIBS setup, but it's something that could be done and is being done. Obviously, the use of LIBS for problem solving in the geosciences has really increased huge in the last 2 decades. There are a lot of reviews coming out from different colleagues. And today, I'm gonna go now to switch to the part of the applications. I just choose some application. I hope you're not gonna get bored too much, but it's just that's probably the most important aspect now to show you what eventually or think about the technique and what you can do. So I'm just reporting here some of my studies performed with the people that I work with in collaboration related to the earth sciences. to the extraterrestrial materials, and even to cultural heritage and archaeology. So the idea, I choose some examples from my previous works and studies published, picking up different applications of setups, LIBS setups, different methods of quantifications, and so on, in order to give you really a broad overview of what is possible, what could be done. So I'll start with some soil analysis and rock analysis. So the first example is this, and it's related to a work regarding the monitoring of heavy metals in some polluted soils from Italy. So I'm just reporting this sketch, not to make it complicated, but just to let you understand, again, remind you a little bit about the use of these setup. So we have our laser here. Again, the beam is coming out. There is a lens focusing the beam on the sample. The sample in this case is a soil. The soil has been pelletized. Okay, so it's a pellet. It's not powder. It won't work. So it's a pellet. In this way, obviously, we are shooting on a pellet. So if we stand in the same position, we're gonna go depth and crack probably the pellet. So the idea was to create a rotating target holder in order that, you know, it's shooting always in a different position. And then obviously we have all the other components that I've been talking before. We have another lens here that is catching this light of the plasma, sending to the fiber, back to the monochromator, ICCD to just get the temporal evolution of the plasma and choose the right timing of acquisition. As you can see here, we were not using, for example, at that time in our benchtop equipment, we were not using the fundamental wavelength. We were using the green, the second wavelength, because this is much more smooth and creating less damages on our samples. There was the choice. Obviously, you lose a little bit in the signal. Maybe it's a compromise. Obviously, you have to be in the lab and try to understand which is the best option. But just to show you that there are also different possibilities. Okay, that's the setup. They've been shown you before. It's just in detail. Here you have the two lasers coming out. The laser beam is coming out from these holes here. And then there is an optical path here. And standing back, this is the spectrometer, the monochromator. This is the ICCD. Here you have the lens that is sending inside the monochromator the light to solve our signal into the spectrum. So we have, I'm not gonna go reading the details because otherwise we will not have enough time, but just to give you an idea, we have these samples here with different texture, different organic matter content, different pH, different total carbonate calcium, and so on. The idea was to analyze those heavy metals, specifically chromium. So now let's see these two spectral ranges, which I'm just taking some portion, you know, of all the spectrum, just to show you where we were able to detect the chromium. Here you can see a nice triplet of 3 emission lines of chromium. But you can see beside there are also other elements coming from the soil, obviously. And here again, there are other 2 peaks of nice peak of chromium. Those 3 are really nice because as you can see, they're just standing alone. We have just a small titanium peak here, but it's not interfering too much. That's consideration for the analytical purposes. Okay, so what we have done is applying the calibration curve method standard. Okay, we have the ICP measurements of chromium, and we will see how we can get our results from the LIBS compared and get quantitative analysis from these samples. And in these first calibration curves, we were able to detect the amount of chromium coming from one sample that was not detected by ICP. So we were able to understand that in this soil, number 4, we have 110 plus minus 20 ppm of chromium. Okay, so now you can say, well, that's good, but who can tell me that it's true this? And it could be every number. So we made a proof and we just extrapolate the sample. We keep out one sample, the S3, out of this curve. So the S3 now here is unknown for us, but we know the composition of chromium. We know that the amount is 530 ppm. And what we made, so extracting, getting out this, we calculate, sorry, it's the opposite, 150 ppm with ICP. And then we calculate from this calibration curve the value of chromium, coming up with, as you can see, a really nice result in agreement with ICP. This is just an example to show you using the calibration curves method to quantification of chromium in soils. And we made the same for lead, zinc, copper, and vanadium. Another example is this one. It's related to the analysis of mercury in the landfill leachates. This time we were using a different setup because we need to, mercury is a tough element to be detected by LIBS. So we need to intensify the signal. We were not able to see a small amount of mercury probably without the intensification of this method. So using 2 laser pulses. In this case, you can see we have one laser here, neodymium YAG, with this wavelength, and the other one is here. They are following different paths, but then they're standing all on the same path in collinear mode. This means that the first one is going, so the 1064, and is producing our plasma. Then after delay time that we choose, we send the other laser, pulse, in order to enhance the plasma, reheat the plasma, and get a better and high intensity signal. So we get this spectra here. We get some, obviously, elements. And as you can see, carbon, magnesium, and so on. But then, here we go. This is the mercury peak that we were looking for our quantification in our study. This is related to 1000 ppm mercury. It's quite high, obviously, but it's still there. And what we made is we create a calibration curve to quantify, and we get nice results. See, the limit of detection was 76 ppm in this case. So this is another example related to soils, but switching to rock analysis and to a different setup of LIBS and a different way also of apply the information coming from LIBS. In this case, we would like to discriminate Kert samples according to their mining site. You will see we have 4 mines, actually 5 mines. They are standing 50 kilometers away, not far than that, in the same region where I came from. These are from Gargan, from the bottom of the boot in Italy, on the hill. You'll see now the map. And then we use, in this case, we use a portable equipment, one of the first commercial ones we used to test it. Here we have our Kert, and then we couple these with machine learning algorithm in order to get some information about mine identification. And let me show you something here. Okay, so we have the samples coming from the mines, from the 5 mines. They were located 3 here, 1 here, and the other one here. So as you can see here, we're standing less than 50 kilometers of distance. So really, even, you have to keep in mind, probably you know better than me also this, that Kert is basically dioxide silicon. So it's not easy to distinguish between some traces elements that could be inside this. So those samples, they might be just similar, totally. It's really hard to distinguish them. So the idea was to apply this in order to discriminate. So the flow chart, we acquire the spectra with LIBS, we pre-process the spectra, we average the data for each mine, we get one just average LIBS spectra coming from many acquisitions. Then we apply the data reduction using the principal component analysis. And then from that, we use the model training, applying different algorithms in order to see which one was standing better for our results. And then we obviously need to evaluate the model to give the proof that this was possible. So here it's a little bit small, but there are some fractions. Every color is standing from the different mines. See 5 different parts of the mines, and different spectral range, highlighting some elements, calcium, barium, sodium, for example, magnesium, iron, and aluminum, and so on. These were used in terms of what we need to do for the algorithms to process and analyze the spectra. So what we get in terms of reduction was this first PCA, looking at just the 3 PCAs here, see it's quite mixed and complex. Then we obviously made a step ahead using the loading plots and seeing the contribution on each principal component, you know, how each element was contributing in this in order to understand which one could be the most important to be discriminating our samples. And we divided the spectral range in 3 ranges, as you can see below here, just highlighting the elements detected. And here we got some confusion matrices. I don't know if you are familiar with this kind of stuff, but I'll give you a quick explanation how to read these. I mean, we have a predicted class. So the predicted class is what is the algorithm suggesting based from the data that we are giving them. This is the true class. In the middle, you have this line in green where it's reporting the samples, okay? So starting from the first column, that's the only example that I'm gonna give, then it's obvious for all the rest. But you will have, in this mine, we came up with exactly 7 samples, okay? See 1, 2, 3 here, and 2 here, 7 samples. We got from mine BRS. The classification and the algorithm was able to give correspondence, and so true class only for 1 element. So on 7 elements, just 1 was identified correctly. The other one, as you can see, those numbers were supposed to be here. But as you can see, 1 sample is standing in this mine, 2, 3 actually in this other mine, and 2 in this other mine. So they were really messing up. We came up using different algorithms, and at the end, we just, in order to shorten, we came up that obviously this one here, you can see the linear discriminant analysis. This is the care near neighborhood algorithm. And again, the linear discriminant analysis, this one just considering the PC2 from the PC10, this one is from the 1 to the 5. But anyway, the most important thing is that the accuracy coming out was 70 here. Sorry, it's covered by this, but it's 70 something here. So not so good. As you can see, these are the good ones. And we came up that excluding the PC1, we were reaching 80. Very, I mean, reasonable, not good, but reasonable considering the similarity of the samples. But why? PC1, why? Why? Because PC1 is given, the most contribution was given by silicon. So we understand that silicon was an interference for the discrimination of these samples, for example. And the proof was also given because that confusion matrix was done 5 versus 5 samples. Then, in order to confirm the accuracy obtained, we used to, go class by class, 1 versus 1 class. So 1 mine versus the other mine, and see what kind of, using different algorithms, what kind of accuracy we were able to reach. And as you can see, if we go in this way, discriminating 1 versus 1, we are able to reach in some of them even 100% of accuracy. So the algorithm is able to discriminate by the spectra exactly the origin of the samples from the mine. Okay, so let's go to the extraterrestrial materials examples. Here again, I'm showing you a different setup again. This is really nice because there is a laser, double laser again, coupled with an optical microscope. It means that the beams are entering inside the microscope. They go through here, and you can shoot directly on your field petrographic section. So the idea was to analyze an iron meteorite. Been studying iron meteorites or meteorites from 10 years more nowadays, and I've been getting more passionate about these samples, and that's why And that's the reason why here you see some examples of these studies. But the idea was to try to use this innovative approach using an optical microscope and shooting directly on the fin section. As you can see here, those are the laser shots. You can see differences sizes on the craters because here I was testing different energies and different conditions in order to avoid to destroy too much the sample. Because keep in mind that since this is a micro-destructive technique, this is one-shot analysis. I mean, one time you shot over there, then you're moving that layer. You're no more acquiring that one, but you're going, I mean, deep. So that is gone. And the idea was to do analysis straight on the bulk meteorite. This is the iron meteorite, and directly on a fin section. Here are just two examples of some spectral ranges related to, in the top here, you can see the bulk, the whole meteorite, and here on the fin section. You'll see that's really a forest of emission lines related to iron. Iron has tens of emission lines. So if you have a soil rich of iron or anything rich of iron, you will see a bunch of emission lines. And here you can see many iron, nickel, cobalt, copper, and so on lines. It's here, down here also the lines emitted from the fin petrographic section. So the idea was to use two different quantification methods. So in this case, see three elements. So we decided to apply the calibration free here. Okay, two methods, different way of applying the calibration. One's the standard calibration free, and then another one called one-point calibration. It's a different version of the calibration free. I'm not gonna go in details here, but it's something that could be used without standards. So the idea was to do these measurements directly on the fin section and on the bulk. And here you can get the results compared with the ICP mass spectroscopy. That is one of the standard techniques used to the characterization and chemical composition for meteorites, and some EDS SEM. And here you have with B, we're talking about the fin petrographic section, and with C is the bulk meteorite. And as you can see, there is a nice agreement. Calibration free is one-point calibration. Those are the two LIBS methods for the quantitative analysis, adapted for the fin section and for the bulk. And even you can see with SEM, using the energy dispersive spectroscopy, you are not able to detect or quantify cobalt because with all these iron, obviously the K alpha of cobalt is covered by iron. So you have to do some deconvolution probably to get information about the cobalt. But that's one example. Another example is still around meteorites, and is the study was suggesting us to use a portable system this time to do analysis straight on the field. Sometimes it's not so easy to recognize visually an iron meteorite in the desert. So the idea was to do a test and see true iron meteorite, a fake, what is called meteor wrong, and this is something coming from the steel, is a slag. It's called pig iron, is a product of industry, steel industry. And make a comparison and try to understand if we are able easily to detect these and quantify also some differences in the element concentration. This is the handheld used for this, was really one of the first commercial produced by BW Tech, was not thought for research at all. And the spectra has limited resolution, I would say, much way better what we have nowadays. But anyway, we were able to distinguish some, or to see some interesting things. So here again, there are some spectral ranges focused. You will see in the blue, it's the meteorite spectra, okay? C, pig iron is the black one, is almost overlapping the suspected meteorite. There is a meteor wrong. The nice thing is that you see nickel, it's not even showing up in these two samples down here, even cobalt and so on. You can see they are really drastically differentiating the two samples, actually the three samples, each other. And the other nice thing is here again, where you can see some emission lines related to titanium and silicon that are strictly related only to pig iron and not even to the suspected meteorite that is just a scoria, an iron scoria from industry, but not containing those elements that are in the pig iron, because we've been working also with the steel industry and doing measurements on pig irons. So what we can get, and I'm showing you some quantitative data. Again, here we apply the calibration free for the meteorite using different techniques. In this case, the differences are just given by using two different setups, LIBS setups. The first one is the one that I've shown before compared to a portable, and see the differences that we can get in terms of quantification. And then here there is a table around some elements much more related to the other two samples, the meteorong and the pig iron, where you can see even the carbon detection, the silicon, manganese, and so on. Okay, so that's the last step, I promise. I hope you can still stand it. I'll be quick. So this study was really nice. We had a project about this. This is the Castello Sveo in Bari, where I live, where I came from. Is made by Normans. And that's the external walls. But our project was related to study these internal walls. Here you can see, that's the wall that I was studying. The first, I mean, this is the combination of two things in this project. I'm going to tell you something more. Maybe you're more interested about these aspects. As you can see here, see these white walls. These white walls were previously black as this one. Those walls were cleaned classically with mechanical techniques. You know, they removed the black crust on the rocks, but really in aggressive way. I mean, the color of the rock, I will not say there is this one, but you know, that sounds good. And even you have to face with the people from the archaeologists and people taking in charge of the monuments. They were really concerned about using to be too drastic. This is really whitish. It's really brilliant white. That's something not related to this rock. That's a limestone from our region. Escaped from our region. So what we were been doing here, we use the laser cleaning technique. So we use laser to remove the black crust on the top of these rocks. So to do this, I had to apply different protocols using different wavelengths and so on. But that's not the story. I mean, then we use also LIBS to do some measurements. In this case, the nice part, because this is the first part, is a part about the project and it's not related to the work that I'm showing you now. Now I'm talking about LIBS. The nice thing that we're doing here is using LIBS to create some images about these rocks. So this is a fragment of that wall. And here you can see clearly how that's really black on the top, black crust, no way. And here you can see the bulk, the white of how it was supposed to be the rock without all the pollution of all these years. So what we were doing was trying to apply one of these figures of merit of the technique. So doing some depth profile and creating a layer, different layers, and see how the elements were changing from the top to the bottom. And that's an example. So black, 5 laser shots, the black. So here I'm just cutting out some region just to highlight some emission lines specifically to the elements related to the pollutions and the rock eventually. And the red one is 75 laser shots consecutive. So 75 going there. These, as you can see, it's clear. Red, it's on the back. There is no iron. It's flat. See, iron is here. And even silicon. There's really small, barely can see it, small peak here in the background. And this is a large, again, example of titanium and even aluminum. So that's just for qualitative idea. Then, what we have done is try to create a three-dimensional compositional imaging of this weather limestone using a double pulse, that equipment that I've shown you before. Thanks to the collaboration, in this case with Vincenzo Pallesti in Pisa, we made together this work. And here you can see the grid of the analytical spots that we used. Okay, it's about 20 micron diameter and space bound about 200 microns. This is a 5 millimeter square surface. So we acquired 625 points and we used 5 double laser shots. Okay, see here, nice to see the square white and like beside the black of the black crust. So we removed totally the black from the rock. And here we have the different slices of the acquisition for each point for carbon, calcium, and iron. Okay, we have laser pulse 1 is the first one here, and then the 2, the 3, the 4, and 5 for the shoots that we used. To do what? So the idea was to create a 3D compositional map. So we plot the intensity of the LIBS emission line of each element at the pixel X and Y corresponding to X and Y steps of our resting. So about 200 micron. The Z coordinate is representing the depth of the laser crater. It's about 1 micron per pulse. So here you see, here we are on the top, okay? The yellow is the most intense presence of iron. See on the top here, that's the first layer. See those highlands here, really intense presence of iron. If you go that, you see it's blue. There is no more, we are here, even zero presence of iron. So that's the idea. And we made this for different elements. Obviously here you can see for calcium, you can see how it's yellow, but here is bright yellow because this is calcium carbonate. So it's covered on the top by the black crust or something. So it's not so intense, but if you go down, it's really intense. And then we come up with this idea about the virtual field section. So what we made, we sliced the compositional map perpendicularly to the sample surface in order to have an estimation of the alteration processes occur at the limestone surface. So this means that here in this color magenta is giving the presence, showing you the presence of the aluminosilicates, obviously presumably coming from the pollution, and the green is the strong presence of carbon. As you can see here, it's also going from the top to the depth inside of the bulk. That's another example. Maybe you will like this more. Going to some artworks coming from, again, from my region. This was a work in collaboration with Girolamo Fiorentino, a friend, an archaeologist from our region. And we had these samples coming from a necropolis, a small town not too far from Bari, on the north of the region. We had these 5 copper alloys objects and those 2 iron alloys. Those are evident even by eyes. So obviously you don't need the technique to understand this. The idea was to apply the use of the handheld, so something that can be easily used in a museum. The idea is thinking that most of the time it's impossible to get out samples from museums. So if we can go there to do the analysis, this will save and maybe discover many things that nowadays we don't know. One example is, I'm not gonna go farther, probably you know, but the use of the X-ray fluorescence, the portable X-ray fluorescence was useful to detect that the Tutankhamun knife and the blade of this knife is made by iron coming from a meteorite. Unless these days we didn't know about that. So those portable techniques and handable techniques, if they could get together, could help really to solve many problems. But here we were focusing on the identification and the inner stratigraphy of those artifacts. We combine the data and the spectra with the graph clustering method, another, chemometric way represented by a cluster that is distinguishing and classifying objects. Okay. So here it's clear and evident. The first two spectra are related to the iron artifacts. See how many emission lines are here and here. And those 5 back here are the copper alloy. See, the elements detected so well for the copper alloy samples, those 5, we detect tin, copper, and lead, basically. And in the iron alloy, iron, for sure, copper, and even a small percentage, less than 100%, 8% of lead. Then we were able to detect other elements, probably from soil contamination of the place where we're escaped, like aluminum, calcium, silicon, and magnesium, and even some trace elements like antimony and zinc. So let's see what we come up from the data analyzed with the graph clustering. That's a mess. I know. I'm trying to explain this. It was not easy even for me at the beginning. What we have here, first of all, let's try to simple things. We have some clusters around here. See, a lot of each of these is related to a spectra acquired with LIBS. Okay, each point of these. So we can see that we have 2 groups here, 2 small groups, 1 big group here, and here quite a messy. See here, they're standing all with 1 letter related to 1 object. Same here. Here we have a mixture of 2 objects, F and G. And here we have even 3 or 4 objects. Okay, so here there is an explanation by those 4 clusters. And what I can tell you is this. The W is the iron alloy artifacts. So it's trying to concentrate all the iron are standing in this cluster. All the objects made of iron, so 2 objects, to be honest, but it's just to give you an idea of the possibilities. We know this. We were able to discriminate this by eyes. So this is not a discovery from this point of view. But what's interesting is what is next eventually. So then we have the Y and the X. So C and E are related to what? To those 2 clusters here, copper alloy. See, they are near, but they are not standing as this one in the same. That's interesting, no? Or maybe it could be. And then we have this, the Z. It's a mess. Other copper alloy objects. So we come up with what? With this. X and Y, so C and E, have the presence of really high intense calcium, silicon, potassium, and sodium in the spectrum. That's a consideration. But what's more interesting is this probably. The proximity is given probably by the presence of antimony in both of them. They were the only samples carrying this element. And the clear separation is due to the high amount of lead in this sample, because this one doesn't have so high amount of lead. That's one point. The other one is related to the object A. See, the object A is going spread from the top. We have 2 groups, one here and one here, but we cannot see a clear separation of the spectra due to the inhomogeneous composition of this sample. So we performed some specific study on the A sample. That's this piece of metal made clearly by eyes, could be easily clearly understandable, made by 3 different pieces of metal. So we decided to go depth here and try to understand what was the composition below the corrosion layer, and trying to understand what these, why, we had this. To do this, we used, 10 micron laser shot. We use 130 almost laser shots to go depth and try to see how the composition was changing with that, with this scheme here. Okay, So what we get is that lamina 1, also on top here, see, it's mainly copper. See the trend with that from starting from the superficial layer to the last one. We had, yeah, a little bit of decrease around 70 to 100 laser shots, but it's quite stable, I would say. And it's also comparable to what we can see in the lamina 2. So this could be given by other reason. Then in the lamina 2 is this small piece here on this side. We can see copper having more or less the same trend, but then we have lead and tin. So we come up that the different composition in the laminas suggest that they were produced at different times and that they were linked together because the object was repaired, probably. And also because we found some confinement of the tin in the innermost layer. So we thought that this was due to the hammering, probably, of these objects once they repaired. So here, just to show you some application done and some micromaps obtained with the handheld LIBS on these two lamina, the 1 and the 2, you can see from the how to read this. The red, the intense red, is the highest presence of the element. The dark blue is from 0. So the dark blue is 0 and the red is 100. So you can see clearly distinction here. Lamina 2 is copper, tin, lead. Here we don't see tin, really few spots of lead, and high concentration even of calcium. Different, you can see different presences of the elements detected. So this is done on a 2 millimeter square map, really small. You can see here some shots to have an idea. On the sample, this is not on the straight sample, but just to give you an idea even of the damage that you can get. That's the last example, I promise. That's some interesting aspect, the use of meteoritic iron for tools in the ancient times. We start studying meteorites in Morocco with some colleagues, geologists, really long time specialists in meteorites. And then we come up also interested to the study of objects made possibly by meteoritic iron. In this case, at that time, there are a lot of people, specifically in Morocco, there is a lot of people familiar with meteorites. So they know that they can do a business. So nomads, they go around the desert looking for objects or eventually for meteorites. I am a member of the Agadir University Museum on Meteorites, and every time that I go there on Tuesday and Thursday, there are long lines standing outside of more than 100 people coming with a bunch of rocks, trying to see if they have discovered a meteorite in order to make some money. So, and they came up also with those nice objects sometimes. There are really rusty stuff. Most of them are blades, as you can see, from knives. This is an axe. But in this case, we got these 5 objects and we start going depth into the studies. We made some preliminary analysis in the past with the portable X-ray fluorescence. But then my idea, obviously, is to use LIBS and try to bring LIBS abroad and try to demonstrate that LIBS could be used as much as possible as X-ray or complementary. Specifically for some aspects could be even more useful. But anyway, since those are not really rare objects like the knife of Tutankhamun, we were able to destroy a little bit those samples in order to create a possible protocol. So what we made here is we just detach and cut a small piece from, I know, archaeologists won't like this probably, and even other people related to cultural heritage, but that's the way how we can, for sure, try to build the protocol and maybe try to adapt these for future studies. The idea was to analyze the really oxidized side and the polished. So we polished one side of the same fragment. So this is the reverse. And we made measurements on both sides. Well, I'm not gonna go see, that's the equipment that I own. It's in our lab in Bari. This is just to show you the raster grid of the laser. You have to keep in mind that in each of these, I'm able to acquire even more than 50 laser shots on average. So it's a huge mole of information. And generally, I use a grid of 12 points around 10 areas. So you can do some calculations about how many spectra I can get in order to homogenize as much as possible and reduce the physical matrix effects. So here we go. I'm just gonna focus on one sample because if you look at the spectra, a bunch of lines, obviously there are 90% of iron, so it's impossible to distinguish something else different. But I'm just focusing on this sample. That is this guy here, this plate. We just cut a little, this is small fragment here on the bottom of the sample. So here, see oxidized side. And as you can see, we have a high amount of nickel, 21 weight %, and even cobalt and iron. Polished side, we have still high amount of nickel, cobalt, and iron. You have to keep in mind that as a geologist, nickel in nature on the earth is no more, even on a mine, higher than 5 weight %. At least, generally is around 2 weight %. No more than that. So this is extremely high. It's something coming from the space. There's no way. Because this is part of an iron meteorite, and generally iron meteorites is a class of meteorites generated by the inside, you know, it's nucleus of protoplanets. That's the story. It's basically how we have, how our planet is done also. So that's all. Obviously, those are the major elements, but there are also trace elements. And that's what we are studying, and that's what we are trying to classify. But that's a long story now. But what I want to show you is the genetic relationships that we are trying to create with this sample eventually. And the other meteorites, one is the one that we have seen studied in the other works that I presented before, Agudal and Nogla Sidi Hali. Those are both coming from the same area, see, not too far from the area where this artifact was found. And here, some comparison with our endowed LIBS, the portable X-ray fluorescence, and the standard reference ICP from the literature. So the iron artifact 5, you will see, is standing really clearly with this meteorite. See the comparison of the numbers. And if you see the other meteorite, it's really low, the amount of nickel compared to this one. And also the amount of cobalt is less than 1 weight %. So we're quite confident. So there are also other elements like oligo elements like gallium, germanium that we are detecting, and specifically for one of that meteorite, because this sample from this artifact number 5 has a high amount of germanium, talking about 2000 ppm, even not common these, and specifically common not in all meteorites, but in a specific class of meteorites. And that meteorite is one of the kind that has really high amount, more than 2000. So there is a strictly genetical relationship with that. So now I'm at the end, finally. Also, LIBS, what I can say is simple and versatile. Simple in the way how you can use the components. You don't have to do too many. You're not producing chemical waste for sure. No using chemical reagents. So it's a green technique, I would say. And you don't need too many components. That's the story. You have to be careful. The only safety, that you have to keep in mind is that obviously those kind of lasers are powerful lasers. So you have, if you're not familiar, generally you're supposed to wear safety protection glasses because it's a class 3B laser, so it can burn your retina unless you're not wearing glasses. But it's something, I mean, if you shoot on your skin, you can burn your skin. So obviously on your skin, it could be really a small damage, but on the eyes, it's really dangerous. You can lose your view. So that's, but compared to X-rays, I mean, we don't have so many restrictions. That's the only one. Obviously, LIBS is still limited, even if the things are growing up usually, but it's still limited about the use in the geosciences. So that's why I'm trying, as a geologist, fall in love with the technique back 20 years ago, trying to spread the word of this technique for what is useful, obviously. So the other point is the historically elaborate technique, but as you have seen, nowadays there are a lot of manufactured commercial equipments and even bespoke LIBS instrumentation for specific geochemical analysis, even in extreme environments. There are a really huge area for routine application, like LIBS across the geosciences, I would say, could be useful for elemental identification and mapping, geomedia classification and discrimination, efficient exploration of mineral resources, or processing, environmental monitoring, and even the cultural heritage. So all of these also is increased by the high performance of those portable and the handheld equipments that we've seen commercialized nowadays. Okay, so I'm just gonna acknowledge some people that were presenting the works that I presented today. Obviously, I'm not doing nothing, I'm doing a part, I'm having an idea, and then we make a co-partnership as usual, trying to bring up all together every one of us with different, experiences and different skills, going ahead and bringing ahead the research. And and that's just if you wanna have an idea. This is a free. I mean, here you can get access. That's something that we build up. Me and another colleague from US. We build up. It's really a list of all the papers related to the geoscience published about the use of LIBS, starting back from the 1990. It's free. You can go there. You can find. I'm updating these every year. So there are all the publications related to even snow, ice, soil, meteorites, soils, and whatever is related to the environment. Those are some references related to my reviews related to this topic specifically. And thank you so much. The last one is doing some publicity about the next book coming, wrote by me and this colleague again, for Cambridge scholars. And it's specifically the first book specifically focused on the use of this technique for the geosciences. So we just try to catch all the things interesting, because the nice aspect is that both of us, we are geologists. He's a retired professor from North Carolina State University. We are both geochemists. We met in 2018 and we just get together with the same idea and start wrote papers and then come up proposing me to write a book, and that's it. That's what we got. It's 400 pages and it's coming next. Thank you so much. So hope that I'm not being too long. I'll try to give you an overview as much as possible what is possible to be done. Thanks again.
Okay. Perfect. Really thanks, Giorgio. It was an amazing presentation. Very, very instructive. Really, we improve a lot about know something more about LIBS, and for sure, during our future collaboration, we can go deeper in for some issue, some material. Okay, just now because it's quite late. If you have some questions in the room, or Mirko, you are online managing the streaming. If there is someone that want to ask to Giorgio, please. Some question in the room? Yes, Andreu. But because you have to come here. If not, the people cannot listen.
Don't be shy.
Cannot listen from there. The people online. Come on.
Well, okay. The question is, for the sample preparation, you said it was for soil samples and rock samples. It has to be pellets, not pulverized sample.
Right. Well, I mean, that was something that I've been always keep thinking to introduce a part regarding the sample preparation, because here there is a legend about this technique. They use that the technique could be used without any sample preparation. I mean, it's true, but until a certain point. Because if you want to reach accuracy and high precision, then you have to do a small preparations. What this means that for sure on powders, this won't be possible because it's the laser, once it's hitting the dust, is gonna pulverize, and so you will have a dust, a cloud dust that is gonna shadowing the plasma and the signal catched by the fiber. So the signal will really decrease. So think in terms of a low content element. This will just disappear. You won't be able to detect. So that's why we are always trying to increase. That's why it's important to have some hard stuff as much as possible, even flat, to optimize the sample. So for soils, essentially you have to work with pellets if you want to get nice results. For rocks, it's a little bit different because a rock, you can even cut the rock, having your flat surface and shoot on the flat surface as I've been showing during the presentation. But for powders, there's no way to get nice stuff. I mean, you can get an idea if you're looking really at something high amount, but it's not the way how you could conduct any analysis.
Okay, thank you.
You're welcome. Thanks for your question.
Okay, thank you. Yeah, there is questions. Okay, from
Carmen.
okay, from Carmen. Carmen, hi Carmen, how are you? There is you can read, yeah, we can read. I have not been for the entire application bit, but are there any example of LIBS applying archaeological prospection, detection site, area of human activity?
Okay, thanks first of all for the question. Yes, I mean, we've been showing some applications in some archaeological sites, not specifically, I don't know what it means for detection of sites. I have no idea if there is a specific meaning for archaeologists about this, but areas of human activity, I mean, if you're thinking in terms of pottery, of any other kind of ornamental objects, or even bones, there are applications. So there is plenty of way to do things. And then, so I mean, could be done, performed inside and even in the lab. I mean, but the good thing is that having portable equipments, you could do a screening and just bring back in your lab essentially what you need that needs a further investigation.
For example, you were yesterday you were telling me about the drones coupled with the LIBS.
Yes,
so
yes,
it's possible to do.
Yeah, that's something that I'm not familiar, and I know that someone is working on that, but it's still something that needs to be developed in terms of technology, at least commercially. But I know that there is people working on that, specifically people also working for all the aerospace applications. The future is that the astronauts supposed to be handing the LIBS instrument and going on the planets, shooting on the ground to get information. That's what they are planning. So I can see that this would be possible.
Okay, thanks, Giorgio. There are any more questions in the room or online? Yeah? No? Okay. So I think that maybe we are going to close the event and just. There is a question. Marisa, in the room.
It's possible to analyze molecules. What is the precedent or what type of molecules have been analyzed?
Well, okay.
Wait, I repeat here. If it's possible to analyze molecules, there is a question in the room.
Well, first of all, thanks for the question. And yes, well, you have to think that the idea is straight from a physical point of view because we are destroying the lattice of our sample. So we're just having essentially electrons, atoms, ions, not even molecules. The detection of molecules, so it's not coming directly by the application, but it's something coming in the post, kind of sort of post-processing, so recombination of the species at the end of the cooling of the plasma. But this is just for the process. So to reply to your question, yeah, it's possible. There is people, and we've been performing some studies regarding carbon, for example, CN and CG. There is people working with calcium fluoride, for example, also, they detected. There are other examples. It's not something so common and familiar, obviously, because you have really to keep and have a nice set of parameters and you have to be specific. And then there are other techniques they could do better. But it's something that in principle is possible.
I was thinking, for example, with pigments in ceramic or
Yes,
yes,
yes.
of course, sometimes I think that the elements perhaps is the more important difference between one pigment and the other.
But
And it's element if
yes.
it's possible to determine. But at the beginning, I was thinking with the possibility to detect determining molecules, but I think that there is principal technique for elements.
Yeah, it's basically for that, but obviously that's something that has been, I'm not so familiar with the study of pigments, to be honest. I've been applying some molecular studies related to soils and to carbon, and we were able to see with two different setups some of those molecules. Just because the issue related to carbon is always related to the fact that generally we are nicely detecting the emission lines of carbon. As you've seen, there are two lines in the spectrum, in the spectral range. One emission line is in the UV, is around 193 nanometers. And this line is just standing alone most of the time. So it's not interfered even by, for example, iron-rich soils. The other line of carbon is 247 nanometers and is in that forest of iron emission lines. So if you have carbon and with a really rich iron soil, you will have a shoulder. So this for quantification would not work easily. And finally, that line, for example, so the idea is that, I mean, most of the people, even ourselves, we studied carbon using those emission lines. But this is not representative of what we were looking, trying to understand the organic, trying to separate the organic from the inorganic part, because that carbon is only the total carbon. So the idea was trying to push a little bit farther and see if it's possible to detect with this technique and distinguish between inorganic and organic carbon. So that's what we've done. I've been also doing some tests on some eggshells from dinosaurs. And that's where, with the handheld, I was able to see some molecular emissions about calcium fluoride. But I've not been going deep into this study. That's only my personal experience, but probably you'll find other literature. We have also a chapter, a section in the book, for example, related to the molecular study of LIBS.
Okay, thanks. Just because I'm reading that someone was not able to hear the answer. So just to remind that we are recording the conference, so we will upload the video in our YouTube channel, and so you will be able to review or listen again the conference, and also are included the question and answer. Okay. At this point, I just was a pleasure. It was really a pleasure to have you here. It was great to listen very interesting things about this technique, your innovation in the field, and just say thanks to the people that were listening and following us online, and the people here in the room. Really thanks, and I hope to see you again here between us in Valencia.
Thank you so much.
Have a